Welcome. We're going to take a quick look at a more geometric representation of the cross product. And so if you look at the diagram on the left, you can see that we have a vector A and a vector B, and then a third vector that's labeled the vector A cross vector B. Keep in mind that the cross product A cross B that vector is orthogonal to both vectors A and B. So the geometric representation has to do with the angle that is separating vectors A and B, and you can see that angle indicated here in the diagram. So it happens to be the case that if I take the magnitude of this vector created with the cross product, the magnitude or the length of that new vector is equal to the length or magnitude of A, vector A, the length or magnitude of vector B, and the sine of this angle that separates the two vectors. So that, again, the length or magnitude of the result of a cross product of vector A and vector B is equal to the magnitude of vector A times the magnitude of vector B times the sine of the angle that separates those two vectors. So let's go ahead and take a look at an example. Okay, so we're going to use this geometric representation to find the angle between the two vectors u and v. Notice in the lower left corner of your screen is the relationship that we had just looked at. So the magnitude of the cross product of vectors A and B is equal to the magnitude of vector A times the magnitude of vector B times the sine of the angle of separation. So what I can do is I can use a little bit of algebra and rearrange this formula and rewrite it as sine of the angle theta. I'm going to divide both sides of that equation by the magnitude of vector A and the magnitude of vector B, which leads me to the sine of theta equaling the magnitude of vector A cross B divided by the magnitude of A times the magnitude of B. Now, we now have a formula that we can use to find the sine of that angle. Once we have the sine of the angle, we can use our knowledge of inverse trigonometry to actually find the angle itself. So we'll go ahead and start by finding this numerator. So we need the cross product of the two vectors and then the magnitude of that. So let's go ahead and do vector u cross vector v. It's going to be the determinant. We'll have vectors, unit vectors I, j, and k. Vector u on the second row. Vector v on the third row. And now we'll go ahead and expand the determinant. We'll have vector I times vector I times negative 1, 4, 2, 5, that determinant, minus, always a minus, vector j with a subdeterminant of 2, 4, 3, 5, plus vector k, subdeterminant 2, negative 1, 3, and 2. So what I end up with is vector I times negative 5 minus 8, so that's negative 13, minus unit vector j times this little determinant, 2 times 5 minus 3 times 4, that's negative 2, plus unit vector k times 4 minus negative 3. 4 minus negative 3 is a 7. So our vector here is negative 13i plus 2j plus 7k. Or in component form, negative 13, comma 2, comma 7 in vector brackets. All right, so that's our cross product. Now we need the magnitude of that. So we'll do the magnitude of u cross v. That's going to be equal to the square root of, we take the x component squared plus the y component squared plus the z component squared. So negative 13 squared plus 2 squared plus 7 squared, which is the square root of 169 plus 4 plus 49, which is the square root of 222. Okay, so now we have our numerator for our formula. Now we need the lengths of the individual vectors. So magnitude of vector u is going to be the square root of 2 squared plus negative 1 squared plus 4 squared. So that's the square root of 4 plus 1 plus 16, or the square root of 21. We need the magnitude of vector v, and that's going to be the square root of 3 squared plus 2 squared plus 5 squared, which is the square root of 9 plus 4 plus 25, and that ends up giving us the square root of 38. So I have all the pieces. So what we could say now is that the sine of the angle that we're interested in is magnitude of u cross v, those are the vectors we're working with, divided by the magnitude of vector u times the magnitude of vector v, which is the square root of 222 over the square root of 21 times the square root of 38, which is basically the square root of 222 over 21 times 38. Now, it does turn out that this fraction can be simplified. Let's see. 2 goes into 222 twice, so we end up with 111. 2 also goes into 38 once. I'm sorry. Let me rephrase that. 2 goes into 222 once. So if I divide 222 by 2, I get 111. I divide 38 by 2, I get 19. Let's try that again. All right, so now we have sine of theta is the square root of 111 divided by 21 times 19. And it turns out that 3 divides into both 111 and 21. 3 goes into 111 37 times, and into 21 7 times. So the sine of our angle ends up being 37 over 7 times 19. 7 times 19 is 133. All right, so that's the sine of that angle, but we were asked to find the angle itself. So now I'm going to use the inverse sine and find that theta is equal to the inverse sine of square root of 37 over 133. Now that is the exact measure of the angle. We should leave it in that form unless we're doing more work with it. It may end up that at some point I might need a decimal approximation, in which case it's fine to go ahead and do that. But if we need an exact answer, this is our exact answer. Now, we could say theta is approximately equal to, if I go to 4 decimal places, 0.5556. But again, that's only an approximation, and we should avoid approximations because errors in approximation can carry forward into problems. And so we keep exact values as long as we possibly can. Now, I want to make one more observation about this cross product and its geometric representation. What I want to do is I want to draw your attention to this diagram we have here. And notice that there is this parallelogram that is can be formed using vectors A and B. What we could do is we could, at the tip of vector A, we could attach an additional vector B, and at the tip of vector B, we could include an additional vector A. And so that creates a parallelogram. And it happens to turn out to be the case that the area of this parallelogram is equal to the magnitude of the cross product of the two vectors A and B. So that magnitude of A cross B is equal to the area of a parallelogram formed from vectors A and B. So when we found the magnitude of the cross product of U and V, what we also found is the area of parallelogram constructed from vectors U and V. That is actually equal to the square root of 222 square units. So an additional geometric perspective on the cross product and the vector that is created. I hope you find this helpful.